next technique here, I don't really have a good name for it. I had the authors, as far as I could tell, the papers I've read, they didn't give it a name, so I call it visualization of relevance. Relevance or distance. In a way, relevance is the opposite of a distance. Uh, the the technique comes from a group in Germany, and they were very interested in databases, in data mining, things along those lines. And the visualization would just help them find clusters and find things that are close together in the database in a kind of highly dimensional space. So consider that we have a kind of high dimensional space. So for the most part, they start, again, being in a database, they start with the query. The query is not that important, but it really, if you want um, an intuition of what the query is, it's like the point of view. It says if you go through in a three-dimensional space and you have a point of view. So your query is where you are in space. Um, it doesn't matter if there's an exact match or not. I know I have it on the slides, but I have a query. I have a point of view in my database. And um, and then what they do is, in this case, the database, you can view each entry, each row in the database as a tuple. So you can view it like that. So that would be the first column of the database, second column, third, and fourth. So in this case, this database has only 4 columns, 4 dimensions. So let's say that's the query. We're looking for something that's 24, 56, and 5. And the thing about all of these other things that I put there, it's kind of trying to explain this notion of distance. So on the first tuple here, there's the difference on the first row is 1, 20 minus 19. The difference here is 0. 4 minus 4 is the same. Difference is 1. Difference is 1. So overall distance is 3. You just add it up. It's nothing very fancier than that. On this second one, all of them, the distance is 3. On this second one, the difference is going to be 20 minus 17. And you take the absolute value. You don't even have to look at positive, negative, but they're all going to be, being a distance is going to be all positive. So the distance is 3. Everything else matches 4, 55, and 6. And on this one, also the distance is 3 because 4 minus 7 is 3. Again, take absolute values. So all of these are at the same distance from my point of view, from my query. So then I don't really understand what they gain from it, but they go ahead and say, we're not going to use the distance, we're going to use the inverse. We're going to do 1 over distance. And they call that relevance. So the smaller the distance, the higher the relevance. And then they kind of go ahead and you want to display this at pixel level. Now, in terms of spatial representation, what happens is you have to consider the overall picture, considering all 4 dimensions, but they also look at individual dimensions. They want to see clusters. And on this next slide, I have, in this case, you can see there are 3 clusters. This is a 2-dimensional space. It's easy to see the clusters. If you go to 4 dimensions, I'm not even sure how you would do it to see the clusters. And like I said, there's other tools to do it. Tisney, for example, or self-organizing maps, they can do. But they're not directly, they might be able to show you cluster. You saw some. But this is another way of showing cluster. The way I like it is because it just uses lots of pixels. Everything it's pixel oriented. Each pixel has a meaning. But anyway, clusters. Because I have 2 dimensions, I really talk about 3 distances. The overall, if you want the relevance, is the overall distance between everything. And then I have a distance on the x-axis and a distance on the y-axis. And here is one point. If you consider it here, you can kind of follow the green arrow. And it's kind of here where my point of view is. It's as if I'm watching this set from that point of view. imagine you're in a room, and again, you can move up in the room, you can kind of go on the ladder, you see something slightly different than if you go down on the floor. And if you move left and right, you kind of get the same idea. So as far as relevance is concerned, I don't know. I didn't order them this way, but I ordered the points in relation to the green arrows. So D is the closest one on the x-axis. F is the, and then you can kind of see the order, F, E, B, C, and A. If you look at the same thing on the on the y-axis, kind of this way, then A and B, C, D, E, and F kind of follow, just because they're, look at their y coordinates. Okay, so you see that clusters tend to stay together, BCA, E and F stay together on most points of view. So that's kind of the idea. Do you see cluster where you see them, are they moving together? Do you have a block that moves? And that kind of tells you there is a cluster, possibly a cluster there. Did the same thing for the black lines. So they're kind of roughly here. So if I go with the order, it's going to be B and E and F. You can kind of see the order right there on the x-axis. And then there's an order over the y-axis. And that's D, C, B, and F. Again, you can see that this one kind of breaks the A, B, and C cluster. It's not necessarily always showing up, but it may be there on the x, especially on the x-axis. But other than that, they tend to stay together. So it depends where you're watching it from. Different points of view, you might see or might not see a cluster. That's another thing here. If you're wondering about the points of view, they kind of have an interface with sliders. You can do it just by moving the mouse up and down. And you also kind of get an idea of their coloring. So everything that's very relevant is going to be yellow. As it becomes less relevant, it's going to get green. And they kind of use this color palette here. You see it. It's further away. So the yellow is a bunch of records that have exactly what I'm looking for on that dimension. In this case, there's 3 dimensions in this view. And then these are records that are close on that dimension, and so forth. You can see as you go further away, it gets really black. So they have like 3 arrangements for these. I only have 2 represented. I kind of figured, hopefully you get the idea. Here is one in which they use a spiral. They take each and every pixel means something. So you would have, and they order the data based on the overall relevance. So this is based on the overall relevance, not per dimension. So all the data points that are very relevant are going to be in the middle. And then they kind of start using pixels and kind of encircling them in this spiral shape. I'm not sure. I need red. So all relevant data in the middle, and then they kind of go around and use pixel next to each pixel. There's no real space in between, so they use each pixel of the screen at that point. And so this arrangement really happens everywhere. So they have one panel for the overall relevance, which almost is like a legend for the color you see. Obviously, they are coloring based on the overall relevance. No, I'm sorry. They're ordered based on the overall relevance. The color is based on whatever each panel does. So in this case, they are ordered by overall relevance and they are colored by overall relevance. So you will see a pretty straightforward pattern in there. You can see easily which yellow would be in the middle and then black would be towards the edges of the panel, smoothly changing. And then for each dimension, basically for each column in my table, they maintain the same position of the pixel, but they vary its color based on the distance on that dimension. Okay, in other words, you can see that the same point is represented in the same place. So this one that I'm doing right now, it's the same point in all 6 views. It may have slightly different colors depending on how far it is on that dimension from my query, from my point of view. And then there's also the red point here. You can kind of see it's the same thing. It's in the same place in all panels. So that is one row in my table, one entry in my database. It's in the same position, but the colors will be different from panel to panel. And here is how this would look like. Like I said, the first one being the whole relevance, it's almost like a, what color did I not use? Let me use orange. It's almost like a legend. You can kind of see things that are really close are this yellow, then you get into a greenish thing, then you get blue, purple, red, and all the way to black. And then you start looking for clusters, and you can kind of see clusters are these blocks, sorry. You can kind of see it here. There's a block, and it kind of corresponds to another block in here. So it's very likely this is there, because they kind of have the same color on 2 dimensions, and even here on this one, they're really far away on this dimension compared to their neighbors. So you see 3 or 4 dimension in which they form a block, then that's likely a cluster. It's not 100% that'll be a cluster, but you can change your point of view and see if that still remains there. So that's kind of what you would look for. So that's a cluster, then maybe that this line here may be part of a cluster. I don't know if it shows up in here. But that's how you would kind of look for them. They're these blocks, squarish blocks that kind of exist there. So that's one representation. Yes. You look at a 10,000 entry database and see all the people that have the same, people that have same characteristics. They tend to have the same median income or whatever. Or look at patients and their vital signs and kind of see age and so forth. And you see where they kind of are grouped together. So this is just plain clustering. So that's the whole idea of clustering, is to find groups of points in a highly dimensional space which kind of are together. So maybe with this, if you consider coronavirus, you will find that people who are over 80 behave differently to the virus than people who are under 30, between 30 and. So that's where, so age would be one of these, and maybe you would see those blocks in there. So it kind of gives you an idea where the clusters are. And you can do it dynamically in the sense that you can move it around and see if that cluster still maintains it if you change your slider a little bit, if you go to a different point of view. So there's other algorithms to do it, but this is a visual way of finding clusters. That's what they're trying to do. That was the practical application of it. Other than, using each and every pixel. There's another way to group this. And here you can see instead, it's still using kind of this concept that, well, it's just going to be a single panel. So for this single panel, you have the first pixel is going to be the overall relevance. Second pixel is going to be dimension 1, dimension 2. So you kind of get a group of pixels. This really works for 5 dimensions. It's not going to work for 6 dimensions. Why? Because 7 is a prime number. You cannot break it down into any block. So this has limitations in terms, you need to come up with these blocks of pixels that have a meaning. And then they use each block kind of gets in here, and they use the arrangement, And you can see how each data point now, it's right next to each other. So it's like taking these and gluing all of them together in one visualization. And here is how it looks like. I'm not sure if it's as clear as the other one. Here you're looking mostly for texture. When the texture changes, you're in a different cluster. You're likely in a different cluster. So the middle, the texture seems to be about the same, but here you kind of see there's texture changes compared to their neighbors. So the dimensions start, the distances start moving, start changing a little bit over there. So that may give you an idea. May find smaller clusters. I don't know. Things that would look possibly too narrow for this visualization here. This can give you smaller clusters, and that's my 2 cents of it. And they have another way of splitting up the space and putting pixels in. So again, for this one, the disadvantage is that you need, it doesn't work for all dimensions, or it works, but you're going to have missing pixels. Like I said, consider 6 dimensions. If you add the relevance, you get number 7. So 7 cannot be divided. It's 7 and 1, that's all. So you're not going to get any kind of block in place. And they've been doing this for databases. They said it can run pretty fast, computing the relevance and all of that. What is the difference? Again, t-SNE, you saw it. It might mess up clusters, but even this one might not give you all the clusters if you have the wrong point of view, the wrong query to start with. But t-SNE is much more modern. I don't know, people in AI like it. For some reason, it caught up with them. It didn't catch up with others, but if you do AI neural networks, they like t-SNE. But you saw that it has problems. Maybe a cluster gets confused between 2 of them. You don't see the concentration of the cluster. So this might actually show you a big change in color on a short range tells you there's not a lot of points there and they suddenly change color. So there's a big distance increase. So they probably all have advantages and disadvantages. All you're trying to do is looking at a highly dimensional data set for clusters. Maybe I should move this. I should move t-SNE down here, so talk about it. Just like the other ones. It's just trying to look at lots of data. Unlike PCP and star plots, they probably won't be able to do 10,000 data points in there. 30, I think that's what they were doing. They were looking at databases with 10,000, 30,000 rows, which is not a big database, but it's definitely not going to fit in a star plot or anything else like that. So that's the advantage of this tool.